March 19, 1941. Inside a drafty warehouse at Quonset Point, Rhode Island, engineer Peter De Jong stares at a problem that will either save thousands of lives or cost them. On the concrete floor before him sits a curved panel of corrugated steel, 32 inches wide, weighing 47 pounds. In 60 days, the United States Navy expects him to transform this single piece of metal into a complete building system that can be manufactured by the thousands, shipped anywhere on Earth, and assembled by men who've never held a wrench. The British tried solving this problem in 1916 and created the Nissen hut, a semicircular steel shelter that kept their troops dry across 2 continents. But the Nissen design carries a fatal flaw that makes it worthless for what's coming. It weighs 3 tons disassembled, requires a wooden skeleton that termites devour in tropical climates, and takes a full week to erect, even with experienced crews. De Jong picks up the steel panel, feels its weight, studies how the corrugations create rigidity from thin material. Somewhere in this curve lies the answer to an impossible equation. How do you create shelter that's stronger than wood, lighter than canvas, and faster to build than both? The clock is already ticking, and nobody in this warehouse knows that in 9 months, Pearl Harbor will burn, and every calculation will become a matter of life and death. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem begins not with engineering, but with arithmetic. By early 1941, the United States military understands war is coming, even if the public remains reluctant to accept it. Naval planners sit in Washington offices surrounded by maps showing the vast Pacific Ocean, and they're running numbers that don't work. If America enters the war, the Navy will need to establish or expand bases across thousands of miles of ocean. Each base requires housing for hundreds or thousands of personnel. Traditional construction methods offer no solution to this scale. A standard wooden barracks building costs $8,000 in materials alone and requires 6 weeks of construction time with skilled carpenters. The Navy calculates that at conventional building rates, it would take 18 months minimum to construct adequate housing for the forces they know they'll need to deploy. That assumes peacetime conditions, available lumber, and no enemy interference. None of those assumptions will survive contact with reality. More troubling, wood construction requires specific grades of lumber that simply don't exist on remote Pacific islands. Shipping lumber across the ocean means using cargo space desperately needed for ammunition, food, and fuel. The whole equation collapses under its own logistics. Canvas tents offer the opposite problem. They're lightweight and pack efficiently, but they fail catastrophically in tropical conditions. Field reports from training exercises in Panama and Hawaii paint a grim picture. Standard Army tents disintegrate under tropical downpours within 3 weeks. Monsoon rains that dump 15 inches in 6 hours turn tent encampments into swamps. The canvas rots, mildew spreads, and within a month, the shelters become health hazards rather than protection. Worse, tents offer zero security for equipment or supplies. A single storm can destroy months of accumulated materiel. Medical officers report that respiratory infections from sleeping in perpetually damp conditions hospitalize more men than training accidents in some locations. The British have been fighting since September 1939, and their experience offers both hope and warning. They've deployed thousands of Nissen huts across North Africa, the Middle East, and Burma. These semicircular corrugated steel structures, invented by Canadian engineer Lieutenant Colonel Peter Nissen during the First World War, represent the first serious attempt at mass-produced military shelter. The Nissen design uses a wooden frame shaped into an arch, with corrugated iron sheets bolted over the frame to create a weatherproof skin. A crew of 6 can erect one in about a week using basic tools, but American observers studying British deployment identify critical weaknesses. The Nissen hut weighs approximately 3 tons when disassembled, requiring mechanical lifting equipment to position the heavy panels. The wooden frame essential to the British design becomes termite food within months in tropical climates. Humidity doesn't just rot the wood, it corrodes the steel fasteners until roofs collapse. Most critically, The Nissen design requires foundation work, concrete pours or substantial wooden platforms, which circles right back to the skilled labor and time constraints the Americans are trying to escape. The ventilation system, adequate for North African deserts, transforms the interior into an oven in jungle humidity. British soldiers in Burma report interior temperatures exceeding 110 degrees, making the shelters unusable during daylight hours. In March 1941, these problems landed on the desk of Rear Admiral Ben Morel, Chief of the Bureau of Yards and Docks. Morel oversees all Navy construction, and he understands the scope of what's required. The Navy isn't just building a few bases, they're creating an entire infrastructure across the Pacific from nothing. He needs a shelter system that can be manufactured in enormous quantities, shipped efficiently, erected quickly by untrained personnel, and survive conditions that destroy conventional buildings. It needs to cost almost nothing and last indefinitely. The specifications sound like an engineering exam question designed to fail students. Morel approaches George A. Fuller Company, a major construction firm already working on the new Naval Air Station, being built at Quonset Point, Rhode Island. Fuller is one of America's premier construction companies, with a reputation for tackling complex projects under tight deadlines. 2 of their men are already on site at Quonset Point working on the base construction. Engineer Peter De Jong has spent 15 years designing industrial structures and understands steel fabrication intimately. Architect Otto Brandenberger comes from an unusual background that will prove decisive. Before joining Fuller, he designed prefabricated farm buildings for the Strand Steel Corporation, agricultural structures that use self-supporting steel arches with no internal framing whatsoever. Admiral Morel's assignment is brutally simple. Design a portable, prefabricated structure that can serve multiple purposes, ship anywhere, assemble quickly, and survive extreme conditions. Have the design finalized and a manufacturing facility operational within 60 days. De Jong and Brandenberger don't refuse because in March 1941, refusing the Navy isn't really an option. They accept the assignment and immediately request the technical drawings for the British Nissen hut. If they're going to improve on an existing design, they need to understand exactly what they're improving. The Nissen hut blueprints arrive within a week, a gesture of wartime cooperation between allies. De Jong and Brandenberger spread the drawings across a work table and begin their analysis. The fundamental concept is sound. The semicircular arch naturally deflects wind and sheds water without requiring complex engineering. The corrugated iron provides weatherproofing, while the corrugations themselves add structural rigidity. But the execution contains multiple fatal flaws for American requirements. The British design treats the corrugated iron as merely a protective skin stretched over a wooden skeleton. If the wooden frame fails due to rot or termite damage, the entire structure collapses. The heavy steel panels require 4 men to lift and position, slowing assembly and demanding more labor. Every connection uses nuts and bolts, meaning assembly time multiplies with each fastener. The 2 small windows adequate for Scottish weather would be completely inadequate for tropical heat. Most fundamentally, the Nissen hut was designed for the Western Front in 1916, where bases remained stationary for months or years. The American Navy needs something that can move with rapidly advancing front lines, be erected in a day, and require 0 skilled labor. Brandenberger's farm building experience offers a radical alternative. His agricultural structures for Strand Steel use corrugated steel panels that are the structure, not just the skin. The steel itself forms a self-supporting arch that requires no internal frame. This violates conventional architectural wisdom in 1941. Architects and engineers think of steel as material for bridges and skyscrapers, massive structures with complex internal frameworks. The idea that thin corrugated steel could support itself seems dubious at best, but Brandenberger has empirical evidence. His farm buildings have survived Midwest tornadoes, ice storms, and decades of agricultural use without internal support. The secret lies in the arch geometry combined with the corrugations. The arch distributes loads along its curve rather than concentrating stress at specific points. The corrugations transform a flexible sheet into a rigid panel through the same principle that makes folded paper stronger than flat paper. Each ridge acts like a miniature beam resisting bending forces. De Jong sees the potential immediately but recognizes the challenge. Scaling up from a farm equipment shed to a military shelter for 36 men means navigating complex structural calculations. Get the dimensions wrong, and the structure either wastes material or collapses under load. The radius of the arch, the spacing of corrugations, the thickness of steel, the method of connecting panels, all these variables interact in ways that must be calculated precisely. They make a critical decision that separates this project from traditional architectural practice. They're not going to design everything on paper first. There's no time. Instead, they'll prototype iteratively, building and testing components in real time, learning from failures, and incorporating improvements immediately. The Fuller Company establishes a production facility adjacent to the Quonset Point construction site. Within 30 days, they erected a sprawling factory building and installed metalworking equipment. The speed is frantic but necessary. They're designing the structure while simultaneously creating the means to manufacture it. The design team expands beyond De Jong and Brandenburger to include several Rhode Island natives with expertise in metalworking. Robert McDonnell, Tomasino Secondino, and Domenic Ergo join the effort. The group works in shifts around the clock, sleeping on cots in the warehouse when exhaustion demands it. The urgency isn't just about meeting the Navy's deadline. Every man in that warehouse understands that war is coming, and when it does, American troops will need shelter immediately. The first major challenge is purely mechanical. How do you bend corrugated steel into a smooth curve without destroying the corrugations that provide its strength? Flat steel can be curved easily through rolling mills, but corrugated sheets resist bending because the ridges want to maintain their shape. Try to force them and the metal buckles or tears. The team consults with Anderson Sheet Metal Company of Providence, Rhode Island, specialists in forming complex metal shapes. Anderson's solution involves passing corrugated sheets through large rollers adjusted to create gradual curvature without crushing the ridges. The process produces what Robert McDonnell later describes as all kinds of tortured squealing as the metal protests that are bent. But it works. The corrugated panels emerge from the rollers, maintaining their structural ridges while conforming to the required 8-foot radius. This single technical breakthrough makes the entire design feasible. The dimensions they settle on emerge from practical constraints rather than aesthetic preferences. 16 feet wide, the maximum that fits on a standard railroad flat car without requiring special wide-load permits. This matters enormously because every hut will travel by rail from factory to port, and special permits mean delays the military can't afford. 48 feet long when assembled from 3 16-foot sections, creating 720 square feet of usable floor space. This allows sleeping quarters for 36 men in double-stacked bunks, with enough remaining space for lockers and a small common area. The arch radius receives 2 full weeks of intensive calculation. Make it too flat, and wind forces could peel the structure open like a sardine can. Too steep and interior headroom disappears, while end-wall geometry becomes impossibly complex. They settle on an 8-foot radius, creating a perfect semicircle. This provides 7-foot headroom where the walls meet the floor and creates what structural engineers term a self-bracing arch. The curve wants to maintain its shape, and when properly anchored at ground level, it distributes loads along its entire length rather than concentrating stress at weak points. Load calculations suggest this design should handle snow accumulation up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. Should. Theory and reality are different things, especially when tropical typhoons and enemy bombing raids enter the equation. But the mathematics support the design, and mathematics are all they have at this stage. By late May 1941, they've fabricated enough components to assemble their first complete prototype. The structure goes up on a concrete pad near the warehouse where 6 sailors, selected because none of them have construction experience, receive 4 hours of instruction on assembly procedures. The Navy wants to verify that ordinary servicemen can actually build these structures without specialized training. The sailors study illustrated instruction sheets, sort components, and begin bolting panels together. Assembly time runs 14 hours, which is both encouraging and inadequate. 14 hours beats the week-long construction time of a Nissan hut, but the Navy specification calls for single-day erection. Marine amphibious operations won't allow multi-day construction projects. Troops hitting a beach need shelter operational before nightfall, not next week. The team studies the assembly process, looking for bottlenecks. The problem reveals itself clearly. The floor system consumes enormous time. The original design includes tongue and groove wooden floorboards meant to create a finished interior surface. These boards require careful fitting, take hours to install, and add £1,200 to the shipping weight. Worse, wooden floors will rot quickly in tropical conditions, possibly faster than the time it takes to ship them across the Pacific. The team debates alternatives before arriving at a solution that demonstrates ruthless engineering practicality. Eliminate the floor entirely from the basic package. The hut sits directly on whatever surface exists, whether crushed coral, compacted sand, dirt, or gravel. The curved steel walls extend all the way to ground level, creating a weatherproof envelope without requiring a finished floor. For applications where finished floors are necessary, hospitals or command centers, those can be added later as separate projects using local materials or specialized kits. But the fundamental shelter achieves its primary mission, weather protection, without floors. This single decision cuts assembly time to 8 hours and reduces shipping weight dramatically. By mid-June 1941, the final prototype stands complete. 96 corrugated steel panels, each measuring 32 inches wide and 8 feet long, weighing less than 50 pounds per panel. 64 steel ribs form the structural skeleton, spaced 3 feet apart along the length of the structure. These ribs aren't load-bearing in the traditional sense. They're organizational elements that help maintain spacing and provide attachment points for interior finishes. The corrugated steel panels themselves carry the actual structural loads. Hundreds of 3/4-inch steel bolts with lead washers connect panels to ribs and panels to adjacent panels, creating a continuous steel shell. The two end walls use plywood, 3/4-inch thick sheets cut to match the semicircular profile. Each end wall includes a standard door and 2 windows, components that can be arranged in different configurations depending on the hut's intended use. Some models get screened windows for tropical climates, others get solid shutters for cold weather deployment. The flexibility is intentional. The Navy wants a single basic structure adaptable to multiple purposes rather than dozens of specialized designs. Total materials cost for this first prototype, $800. Total weight when disassembled, 9,000 pounds. The entire kit packs onto a single standard flatbed railcar measuring 40 feet long. Compare this to a Nissan hut at 3 tons requiring multiple railcars, or conventional barracks construction requiring lumber shipments measured in hundreds of tons. The efficiency isn't an incremental improvement, it's revolutionary. But impressive prototypes and proven field performance are entirely different things. The Navy isn't going to stake thousands of lives on mathematical calculations alone. They demand comprehensive testing under conditions matching what these structures will actually face in combat zones. Navy structural engineers arrive at Quonset Point with wind load tables, typhoon data from Pacific meteorological stations, and a fundamental skepticism about whether this corrugated steel tunnel can actually survive what nature and enemy action will throw at it. The testing data they bring isn't theoretical. It comes from real disasters. Typhoon Gloria struck Guam in November 1940 with sustained winds of 140 miles per hour and gusts reaching 180. That storm destroyed 80% of the wooden structures on the island and turned corrugated metal roofing into airborne razors that decapitated palm trees. The 1935 Labor Day hurricane that killed 400 people in the Florida Keys produced winds powerful enough to sandblast paint off buildings, drive wooden planks through palm trees like spears, and derail a rescue train attempting to evacuate residents. If Quonset huts fail under similar conditions, the result isn't just property damage. It's dead servicemen and destroyed equipment. The structural analysis begins with fundamental physics of arch behavior. When wind hits a flat vertical wall, it creates what engineers call a pressure coefficient. The wind pushes directly against the surface with maximum force. A rectangular building essentially offers a solid barrier that wind must either push through or flow around, and the energy of that interaction creates enormous stress on the structure. Flat walls can be torn away, roofs lifted off, entire buildings collapsed if wind forces exceed the strength of connections. A curved surface changes everything. When wind encounters the Quonset's semicircular profile, it doesn't slam into a barrier. Instead, the curve deflects the wind upward and around, reducing direct pressure dramatically. Think of water flowing around a smooth river stone versus hitting a dam wall. The stone experiences minimal force because water follows its contours. The dam wall absorbs massive pressure because it blocks the flow. The Quonset hut functions like that river stone, letting wind slide over its surface rather than resisting it through brute strength. The corrugations add a second layer of structural intelligence. Those ridges running lengthwise aren't decorative. Each corrugation acts like a miniature I-beam, the cross-sectional shape that maximizes strength while minimizing material. An I-beam resists bending because its shape distributes stress across the entire cross-section rather than concentrating it at a single point. The corrugated panel achieves the same effect. Bend a flat sheet of paper and it folds easily. Corrugate that same paper by making accordion pleats, and suddenly it resists bending in the direction perpendicular to the corrugations. The arch geometry creates what structural engineers call a compression ring. In a conventional rectangular building, the roof pushes down on walls, walls push down on foundations, and everything depends on vertical load paths remaining intact. Storm winds can lift roofs off because they're essentially separate elements just sitting on top of walls. The Quonset design eliminates this vulnerability entirely. The arch is a continuous curve where every panel shares loads with its neighbors. Forces don't concentrate at corners because there are no corners. Wind pushing on one section gets distributed around the entire ring. The hoop stress, the tension trying to spread the arch apart at ground level, gets resolved by the ground itself. Each panel bolts to adjacent panels with connections spaced every 6 inches, creating what amounts to a 48-foot steel cable wrapped into an arch shape. This cable wants to maintain its curved form. When properly anchored at ground level, the arch becomes extraordinarily resistant to deformation. But theoretical analysis only goes so far. The Navy demands empirical validation, structures tested to failure under controlled conditions. They establish test facilities at the Davisville site and begin subjecting prototype huts to increasingly severe abuse. Wind loading tests use massive industrial fans to generate hurricane-force winds. Engineers measure deflection, monitor stress at panel connections, and look for failure modes. The structure flexes slightly under extreme wind, which is exactly what it should do. Rigid structures shatter. Flexible structures survive by absorbing and redistributing forces. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Snow loading tests pile sandbags on the roof until the structure either holds or buckles. The design proves capable of supporting 40 pounds per square foot, adequate for any climate American forces are likely to operate in. More elaborate tests involve dropping weights to simulate bomb concussion, setting off explosive charges nearby to measure blast resistance, and subjecting the structure to water spray that simulates monsoon downpours. The galvanized steel sheds water perfectly. No leaks develop at panel joints. The structure performs as designed. The most valuable test data comes from an unexpected source. In March 1943, a massive nor'easter struck the New England coast with 75-mile-per-hour winds and heavy snow. By this point, several Quonset huts have been erected at the Davisville facility for various administrative purposes. Engineers have instrumented one with strain gauges and deflection meters specifically to capture real-world performance data. The storm provides perfect test conditions, sustained high winds combined with significant snow accumulation. The instrumentation records the structure flexing less than 2 inches at its crown, the highest point of the arch, during peak wind gusts. When winds subside, the arch returns to its exact original shape with zero permanent deformation. Panel connections show no signs of stress. Nothing leaks. The structure behaves precisely as mathematical models predicted. This empirical validation proves crucial because it confirms that the design isn't just theoretically sound, it actually works under conditions that destroy other structures. Tropical environment testing poses different challenges. You can simulate wind and snow in Rhode Island, but you can't replicate years of jungle exposure. The corrosive effect of saltwater air, the rot caused by perpetual humidity, the damage inflicted by insects and fungus, these require actual tropical conditions over extended time. The Navy ships test units to the Panama Canal Zone, where humidity averages 85% year-round, temperatures stay above 80 degrees, and saltwater air corrodes everything metal. 6 months later, the Panama report arrives. Minimal corrosion on galvanized steel panels, no structural degradation. But there are serious problems with interior condensation. When hot, humid air enters the hut and encounters the relatively cooler steel at night, water vapor condenses and literally rains from the ceiling inside the structure. Troops waking up to water dripping on their faces aren't going to consider this adequate shelter, regardless of how well it survives typhoons. The solution requires adding ventilation louvers at both ends and along the ridge line. These openings let hot air escape while drawing cooler air in from ground level, creating continuous air circulation. The vents must be designed carefully to allow airflow without compromising weather protection or structural strength. Too large and rain drives through, too small and air doesn't circulate adequately. The final design uses angled louvers that shed water while maintaining airflow, adding $47 to unit cost, but transforming the hut from a steel sauna into habitable space. The foundation question generates surprising debate. How do you anchor a 9,000-pound building to loose sand or coral without pouring concrete? Foundations? Concrete requires water, cement, aggregate, mixing equipment, and time to cure. Everything the Quonset design is meant to eliminate. The team explores multiple approaches before adapting technology from tent anchoring scaled up dramatically. Heavy steel stakes, 18 inches long and half-inch diameter, drive into sand or soft ground. Steel cables connect stakes to the hut's base, creating tension that resists uplift forces from high winds. For harder surfaces like coral or rock, the design includes bolt patterns that let the structure mount directly to wooden sleepers, heavy timbers laid on the ground, or to pierced steel planking, prefabricated steel mats developed for temporary airfield construction. The beauty of this system lies in its forgiveness. The structure can flex slightly with ground movement, thermal expansion, or settling without tearing itself apart. Rigid foundations crack. Flexible anchoring survives. By late June 1941, the design reached maturity. The War Production Board, the federal agency coordinating military manufacturing, approves Quonset hut production and authorizes contracts with multiple manufacturers. What happens next demonstrates American industrial capacity, operating at levels that would seem impossible if the documentation didn't exist to prove it actually happened. The Navy contracts with 10 major steel fabricators across the Midwest and Northeast. These companies were making grain silos, water tanks, agricultural buildings, and industrial structures 6 months earlier. Now they retool entire factories for exclusive military shelter production. The Strand Steel Corporation, the same company where Otto Brandenburger designed farm buildings, converted its facility outside Philadelphia. George A. Fuller Company, the original developer, takes over a former automobile parts plant in Chicago. Great Lakes Steel dedicates 2 rolling mills to nothing but corrugated panel production. The manufacturing process draws directly from automotive assembly line principles that Henry Ford pioneered in the 19-teens. Raw materials enter one end of the factory, finished products exit the other, with each station performing specific operations in sequence. Massive steel coils arrive by rail. Each coil measures 4 feet wide and contains enough material for 30 panels. These coils feed into rolling machines that corrugate flat steel, creating structural ridges spaced precisely 2 2/3 inches on center. The machines operate continuously, producing corrugated sheets at rates that would have been unimaginable just years earlier. The corrugating process itself work hardens the steel, a metallurgical effect where deforming metal at room temperature increases its strength. The corrugated panel emerges stronger than the flat sheet that entered the machine. From corrugating, panels move to cutting stations where they're sheared to precise lengths. Then comes galvanizing, perhaps the most critical step for ensuring long-term durability. Galvanizing involves dipping steel panels in molten zinc heated to 850 degrees Fahrenheit. This isn't painting or coating, it's a metallurgical bond where zinc atoms fuse with surface iron atoms, creating an alloy layer that sacrifices itself to corrosion before the underlying steel can rust. In saltwater environments, this zinc coating makes the difference between a 5-year lifespan and a 50-year lifespan. The cost adds $112 per hut, but field reports from Pacific deployments prove the expense is essential when ungalvanized steel corrodes through in 8 months of exposure. Quality control operates on principles unusual for 1941, but standard in modern manufacturing. Every batch of panels undergoes testing. Samples get measured for gauge thickness, corrugation spacing, coating weight. The military specifications are strict because lives depend on these components, performing as designed. Panels that fail inspection get scrapped and recycled. There's no tolerance for substandard materials when the product will be keeping American troops alive in combat zones. Each complete hut kit gets packaged with obsessive attention to shipping logistics. The 96 corrugated panels nest inside each other like stacked bowls, a packaging innovation that reduces crate height from 8 feet to just 14 inches. This matters enormously because cargo space on ships and trains is measured precisely. Wasted space means fewer huts delivered, which means troops without shelter. The end walls, plywood sheets pre-cut with door and window openings, pack flat between the nested steel panels. All fasteners, bolts, nuts, washers, stakes, and hardware go into a single wooden crate that also contains illustrated assembly instructions. These instructions use minimal text with maximum visual clarity, designed for men who might not read English fluently or who have limited construction experience. The illustrations show each step in the assembly sequence with numbered parts and clear diagrams. It's technical communication designed for battlefield conditions where nobody has time for ambiguity. The entire kit loads onto one standard flatbed railcar measuring 40 feet long. This dimensional constraint was fundamental to the original design. American railroads use standardized equipment, and anything requiring special handling creates delays. The Quonset kit fits standard infrastructure, meaning it can move through the transportation network as efficiently as any other cargo. From factory to rail yard to port to ship to destination, the package dimensions remain compatible with existing handling equipment. The shipping choreography operates at a stunning scale. Trains leave Philadelphia, Chicago, Pittsburgh, and Detroit daily, carrying hundreds of hut kits westward. They arrive at San Francisco, San Diego, Seattle, and other West Coast ports where Liberty ships and specialized cargo vessels wait at dock. Longshoremen load complete huts into ship holds using the same crane systems designed for tanks and artillery pieces. A single Liberty ship can carry 200 Quonset huts, plus their assembly hardware, representing shelter capacity for 7,200 men. The War Shipping Administration, the federal agency managing merchant marine operations, tracks every manifest with the understanding that cargo priority directly affects combat effectiveness. A hut shipping to Guadalcanal in September might house a bomber crew by October, making the difference between operational aircraft and pilots sleeping in muddy foxholes. These aren't just buildings being shipped, they're strategic assets that enable military operations. December 7th, 1941, changes everything. Pearl Harbor burns, and within 72 hours the logistics nightmare transforms from theoretical planning problem to immediate crisis. Japanese forces sweep across the Pacific. Wake Island, Guam, the Philippines, all come under attack simultaneously. American troops need shelter everywhere at once. The War Department increases Quonset production targets from 40 units daily to 150, then higher still, as the scope of Pacific operations becomes clear. The production network responds with speed that seems impossible unless you understand how thoroughly American industry had already been preparing. By August 1942, the 10 contracted factories collectively produced 1,500 complete huts weekly. That number keeps climbing. New manufacturers join the program. Butler Manufacturing Company begins producing an alternate design called Butler Huts. Armco International Corporation makes heavy steel versions intended for ammunition storage and bomb shelters. The Pacific Hut Company in Seattle manufactures wooden versions for locations where steel is unavailable. By December 1943, monthly production reached 8,000 units. The logistics network moves so efficiently that huts ordered in Pennsylvania arrive in New Guinea within 40 days, including ocean crossing and trans-Pacific transport. Think about what that means operationally. Engineers in Rhode Island finalize a design improvement in early January. Factories incorporate the change by mid-January. Ships carry the improved huts across the Pacific through submarine-infested waters in February. Construction battalions assemble those huts on newly captured islands in March. From design modification to operational deployment in 90 days while fighting a global war, the cost accounting tells the story plainly. Each Quonset hut provides shelter for 36 men with materials costing $800 and requiring approximately 60 man-hours of assembly labor using unskilled personnel. Compare this to conventional barracks construction. $12,000 in materials, 400 man-hours of skilled carpentry, 6 weeks construction time, and vulnerability to termites, rot, and weather damage that destroys the building within years. The Quonset delivers shelter at 1/10 the cost in 1/20th the time, with 50 times the durability. But numbers on spreadsheets don't capture what these structures mean to men sleeping in them. The real test comes in combat zones, where theory meets reality and inadequate equipment kills people. Guadalcanal provides that test in August 1942, when the first combat-deployed Quonset huts arrive on a beach where temperatures hover at 95 degrees, with 90% humidity, and Japanese bombers make daily visits to create anything that looks like American infrastructure. Marine engineers unload flat-packed steel panels under sporadic artillery fire and start bolting them together in a coconut grove, still showing scorch marks from the previous week's shelling. The assembly crews work in rotations because no one can function for more than an hour in that heat wearing helmets and carrying rifles. But the work proceeds. No cranes needed, no concrete mixers, no specialized tools, just wrenches, determination, and illustrated instructions. Within 12 hours of the first panels coming ashore, Henderson Field has 10 new structures housing maintenance crews for the battered F-4F Wildcat fighters operating from the Coral airstrip. The crews sleep on cots inside curved steel walls, while Japanese artillery shells impact in the jungle close enough to feel the concussion. The huts provide psychological shelter as much as physical protection. Having a roof overhead, even a steel one that radiates heat like an oven, makes a difference to men who've been sleeping in foxholes for weeks. The real test comes 3 days later, when a Japanese bombing run scores a near miss. A 500-pound bomb detonates 40 yards from a hut full of aviation mechanics who are rebuilding a damaged aircraft engine. The blast wave flattens surrounding palm trees, shreds canvas tents like tissue paper, and drives coral fragments through wooden crates. The Quonset hut flexes. Dirt and shrapnel rattle off the corrugated steel like hail. The structure shifts slightly on its foundation but holds together. When smoke clears, the mechanics emerge shaken but alive. The aircraft engine they were working on, protected inside the hut, is undamaged and operational within hours. That single incident validates every calculation, every design decision, every hour spent testing in Rhode Island. The structure performed exactly as intended, absorbing and redirecting blast forces through its arch geometry rather than shattering like a rigid building would. The after-action report notes clinically that canvas tent occupants in similar proximity to the blast suffered 75% casualties. Quonset hut occupants, 0. That data point circulates through every combat theater within weeks. The jungle environment proves as hostile as enemy action, but in different ways. Within 2 weeks of deployment, Red rust streaks appear on any hardware that wasn't galvanized. The salt air, carried inland by constant wind, corrodes standard steel fasteners like acid. Fungus grows on every surface that holds moisture, turning the interior walls into abstract exhibitions of black and green mold that makes men sick. The ventilation louvers that seemed adequate in Rhode Island testing barely move the suffocating tropical air. Marines start propping doors open 24 hours a day, despite security concerns about light discipline during blackout conditions. Some crews cut additional ventilation holes with tin snips, violating structural specifications, but making the huts survivable in 100-degree heat. These field modifications get documented in detailed reports sent back to Quonset Point. Engineers incorporate the lessons into later production runs. More ventilation, larger louvers, and every single fastener galvanized regardless of position or apparent exposure. The design evolves continuously based on what works and what fails in actual combat conditions. Iwo Jima in February 1945 provides a different kind of hell. The volcanic island offers black sand that blows into every crevice, no topsoil for grounding stakes, and constant threat of artillery from Mount Suribachi. Construction battalions arrive on D-Day +2 and start assembling Quonset huts under fire, literally bolting panels together while mortar rounds impact 200 yards away. The volcanic sand proves impossible for traditional stake anchoring. Metal stakes just pull out of the loose material when any lateral force is applied. Crews improvise by filling empty 55-gallon oil drums with sand and connecting steel cables from drums to hut bases. These improvised anchors weigh 600 pounds each, enough mass to resist wind uplift when properly positioned. When a Pacific typhoon hits in March, with winds measured at 110 miles per hour, those improvised anchors hold while wooden structures across the island disintegrate into flying debris. The base commander's report to Pearl Harbor headquarters is succinct. Quonset huts survived. Everything else was destroyed. The Aleutian Islands campaign tests the design from the opposite extreme. Alaska's frozen archipelago sees Quonset deployment at Dutch Harbor and Adak, where temperatures plunge to -40 degrees and winds regularly exceed 100 miles per hour. The extreme cold makes the steel brittle. Early units suffer cracked panels at bolt holes, where stress concentrates during contraction and expansion cycles. The solution requires specifying different steel alloys with better low-temperature performance and adding rubber gaskets at every joint to maintain flexibility. Heating the huts creates its own problems. Warm interior air meeting frozen exterior steel produces condensation that literally rains inside, until crews learn to install insulation blankets between the steel skin and interior wall panels. The insulation must be carefully designed to prevent moisture from accumulating within the wall assembly, where it would freeze, expand, and eventually destroy the structure from inside out. By winter 1943, cold-weather Quonset models include internal insulation batting, double wall construction for extreme cold zones, and modified ventilation systems that prevent heat loss while managing moisture. North Africa and Italy introduce yet more variables. At Palermo, Sicily, a Quonset pressed into service as an ammunition depot takes a direct hit from a German 88mm artillery shell. The shell penetrates the steel skin, detonates inside among crates of small arms ammunition, and the resulting explosion should theoretically vaporize North Africa and Italy, introduce yet more variables. At Palermo, Sicily, a Quonset pressed into service as an ammunition depot takes a direct hit from a German 88mm artillery shell. The shell penetrates the steel skin, detonates inside among crates of small arms ammunition, and the resulting explosion should theoretically vaporize the structure. Instead, the arched shape channels blast force outward through the walls and roof in a pattern that leaves the structural frame twisted but standing. Explosive ordnance disposal crews, examining the wreckage, note that a rectangular building would have collapsed completely, burying anyone nearby under tons of rubble and trapping fire inside to consume everything. The arch's inherent strength, that compression ring effect distributing forces around the entire curve, means even catastrophic damage doesn't trigger total structural failure. The building absorbs punishment and remains partially functional rather than shattering into fragments. The Pacific typhoon season of 1944 delivers the ultimate stress test. Super Typhoon Cobra hits the Philippines in December, with sustained winds measured at 140 miles per hour and gusts exceeding 160. Storm surge reaches 20 feet, flooding coastal installations and drowning men in their bunks. At Tacloban, the typhoon destroyed 80% of all structures on the base. Wooden buildings explode into splinters that become airborne projectiles. Concrete block structures collapse when wind and water undermine their foundations. Metal roofing peels away and flies hundreds of yards, slicing through anything in its path. Of 43 Quonset huts on the base, 39 survive intact. 4 suffer repairable damage, bent panels and torn seams, but no total failures. Engineers analyzing the survivors identify that proper anchoring matters more than any other factor. Huts with adequate ground attachment ride out the storm. Those with improvised or insufficient anchoring tumble like massive steel tumbleweeds, destroying themselves and anything they impact. The lesson gets incorporated into repair field manuals immediately. Anchoring specifications become mandatory rather than suggested, with detailed requirements for different soil and weather conditions. By war's end, field performance data from 50 combat zones feeds back into continuous design improvement. The 1945 production models bear little resemblance to the 1942 prototypes. Better ventilation with adjustable louvers that can be opened in tropics or sealed in Arctic conditions. Stronger fasteners using hardened steel that resists corrosion and shock loading. Improved insulation options, including reflective barriers that reduce radiant heat transfer. Modular interior wall systems that let crews configure the space for different purposes without cutting into structural elements. Field-tested modifications that transform a good design into an exceptional one proven under the worst conditions imaginable. May 8, 1945. Victory in Europe. August 15, 1945. Victory over Japan. Suddenly, the United States military owns approximately 170,000 Quonset huts scattered across 6 continents and faces an unexpected question. What do we do with them now? The original planning assumption held that these were temporary wartime expedients to be scrapped or abandoned once permanent facilities could be built. But something unexpected happens. Nobody wants to discard them. At hundreds of military bases slated for closure or downsizing, commanders look at their Quonset huts and see not obsolete wartime relics, but perfectly functional buildings that cost almost nothing to maintain and adapt to virtually any purpose. The War Assets Administration, the federal agency tasked with liquidating surplus military property, finds itself managing an unusual problem. There's more demand for used Quonset huts than available inventory. Veterans returning home discover a housing shortage so severe that families live in converted chicken coops, share apartments with 3 other families, or sleep in cars because rental housing simply doesn't exist. The construction industry, starved of materials and labor during 4 years of total war mobilization, cannot build fast enough to meet demand. Material shortages persist well into 1946 as factories retool from military to civilian production. Skilled construction workers are scarce because millions of men are still being demobilized from military service. Into this crisis steps the Quonset hut, now available for civilian purchase at liquidation prices ranging from $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally, if you could even find contractors available. The federal government actively encourages this repurposing through programs prioritizing veterans for Quonset purchases. By late 1946, entire suburban developments made exclusively of Quonset huts spring up around major cities. Roger Young Village in Los Angeles houses 750 families in converted military huts arranged in neat rows with shared community facilities. Each family gets 480 square feet of living space, cramped by peacetime standards, but palatial compared to the alternatives. Residents plant gardens, paint their steel walls cheerful colors, and build conventional-looking porches that disguise the utilitarian military origins. Vetville developments appear near universities where the GI Bill floods campuses with students needing immediate housing. The University of Iowa establishes Quonset Park, married student housing consisting entirely of military surplus huts. Yale used them for student accommodation well into the 1960s. These aren't considered desirable housing by residents who dream of traditional homes with actual bedrooms and proper kitchens. But they're affordable, available immediately, and adequate for young families building their post-war lives. The architectural adaptations get creative rapidly. Families add wooden facades to the curved ends, making structures look less like military surplus and more like quirky cottages. Interior walls divide open space into bedrooms, living areas, and kitchens, using conventional framing and drywall. Windows get cut into steel sides, technically violating every structural principle, but making spaces actually livable for domestic life rather than military barracks existence. Some owners go further, burying entire structures halfway into hillsides for earth-sheltered insulation or connecting multiple huts end to end, creating sprawling compound homes. Housing inspectors and building code officials initially resist approving these modifications. The structures don't conform to residential building codes written for conventional wood frame construction, but the housing shortage is so desperate that municipalities reluctantly grant permits. In Portland, Oregon, an entire neighborhood called Fairview Addition consists of 350 Quonset homes. What begins as temporary housing gradually becomes permanent as residents invest in improvements. By the 1950s, many of these huts had additions, gardens, and landscaping that completely transformed their appearance. Churches discover Quonset huts solve a different problem entirely. Post-war suburban expansion creates new congregations needing worship space immediately, but lacking funds for traditional church buildings. A conventional church requires fundraising campaigns lasting years or decades before construction begins. A surplus Quonset hut costs $2,500 and provides worship space next month. First Presbyterian Church of Levittown, Pennsylvania, holds services in a Quonset from 1952 until 1967, when they finally raise funds for a traditional sanctuary. Dozens of congregations make identical calculations. The acoustics are terrible, the curved walls create strange sightlines, and the utilitarian aesthetic hardly inspires religious contemplation. But people can gather for worship immediately, instead of waiting years for ideal conditions. Some of these temporary church huts remain in service for 30 years, outlasting the generations who first considered them stopgap solutions. Several congregations eventually build traditional sanctuaries but retain their original Quonsets for Sunday school classrooms or fellowship halls, the buildings becoming part of church history and identity. Education sees similar adoption patterns. Post-war school enrollment explodes as the baby boom hits, and school districts face impossible mathematics. They need classrooms immediately, but conventionally built schools take years from initial planning through construction completion. Rural districts especially embrace Quonset classrooms, where a single hut provides space for 30 students at 1/10 the cost of traditional construction. By 1950, an estimated 3,000 schools across the United States include at least one Quonset classroom in their facilities. Some students spend entire elementary educations in these steel tunnels, learning multiplication tables and American history under curved ceilings that once sheltered bomber crews in the Pacific. Teachers hang maps and posters on interior wall panels, install chalkboards, and arrange desks in rows, just like conventional classrooms. The structures prove surprisingly adequate for education despite never being designed for that purpose. Good acoustics for a classroom require sound absorption. Steel and masonite provide almost none, but teachers adapt, speaking clearly and maintaining discipline to manage the reverberant space. The commercial sector recognizes opportunities quickly. Small businesses, machine shops, auto repair garages, warehouses, farm equipment, storage operations understand that Quonset huts deliver clear span interior space without support columns, making them perfect for industrial work. A welder can set up a complete shop in a surplus hut for less than 2 months' rent in conventional commercial space. The structures require minimal foundation work, no complex permits, and assemble in days rather than months. Agricultural use proves especially popular and enduring. The original Strand Steel Corporation, having contributed to military Quonset design, returns to manufacturing civilian versions specifically marketed to farmers. Thousands of Midwestern farms add Quonset storage buildings for grain, equipment, and livestock shelter. The maintenance requirements are minimal. Hose off the exterior once yearly to remove accumulated dirt, check bolts occasionally for looseness. The galvanized steel coating protects against rust for decades. Farmers who purchased surplus military Quonsets in 1946 often find them still functional and useful in 1976, 30 years later, with essentially zero maintenance costs. This civilian adoption creates an accidental architectural legacy. Quonset huts become embedded in American visual culture as symbols of practicality over pretense, function over form, and resourceful ingenuity, making do with what's available. They appear in movies, television shows, and photographs as shorthand for post-war optimism mixed with austerity. The curved steel profile becomes instantly recognizable, even to people who never experienced the wartime or immediate post-war era. Architectural historians initially dismiss Quonsets as temporary eyesores unworthy of serious study. But by the 1990s, preservationists began recognizing surviving Quonset huts as important examples of adaptive reuse and vernacular architecture, representing a unique moment when military technology successfully transitioned to civilian life. Several achieve historic landmark status, protected as representing industrial design, innovation, and social history. The CB Museum in North Kingstown, Rhode Island, preserves original Quonsets as part of its permanent collection, celebrating both the structures themselves and the construction battalions that erected them worldwide. Modern disaster relief operations reveal why Quonset design principles keep reappearing in 21st century emergency response. When the 2010 Haiti earthquake destroys Port-au-Prince, relief organizations face identical equations that confronted American military planners in 1942. Immediate shelter for hundreds of thousands of displaced people, no existing infrastructure, no time for conventional construction, conditions that destroy inadequate temporary housing within months. The solutions that emerge borrow directly from Quonset principles, even when designers don't consciously realize they're channeling 1940s military engineering. Arched steel frames supporting corrugated metal panels, prefabricated components that ship flat and assemble quickly. Self-supporting structures requiring minimal foundation work. The basic formula hasn't changed because underlying physics and logistics haven't changed. The United Nations High Commissioner for Refugees currently uses shelter systems called refugee housing units that are essentially Quonsets, with 80 years of material science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, they employ snap-fit connections. But the core concept remains identical: curved profile for structural efficiency and wind resistance, self-supporting arch eliminating internal framing. Flat pack shipping allows massive quantities to reach remote locations. Assembly by unskilled labor with minimal tools. A two-person crew can erect a modern refugee housing unit in 4 hours, almost exactly matching 1942 Quonset specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, the Middle, East, and Asia, proving that the design solves fundamental human needs as effectively now as 80 years ago. Hurricane-resistant construction has rediscovered arch geometry after decades of building conventional rectangular structures that hurricanes repeatedly destroy. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers studying which buildings survived found curved structures consistently outperformed rectangular ones. The Mississippi coast saw entire neighborhoods of conventional homes reduced to concrete foundation slabs, while a handful of Quonset-style metal buildings stood intact with minor damage. This empirical evidence triggered research into aerodynamic architecture, designing buildings that work with wind forces rather than resisting them through brute strength alone. The results look remarkably similar to Quonset huts because physics hasn't changed. Wind flowing over curves creates less pressure than wind impacting flat surfaces, Today, exactly as in 1942, several companies now manufacture arch-roofed prefabricated cabins using corrugated metal and self-supporting curves that Otto Brandenberger pioneered. These sell to buyers seeking affordable housing, disaster-resilient structures, or off-grid living solutions. Perhaps the ultimate validation comes from space exploration, where NASA and private space companies designing Mars habitats keep independently arriving at Quonset-like solutions. Proposed Martian shelters feature arched profiles to resist severe dust storms, prefabricated components that ship on spacecraft with extreme weight and volume constraints, self-supporting structures that don't require extensive foundation work in Martian regolith. The constraints of interplanetary construction mirror Pacific theater, challenges of 1942 so precisely that engineers independently rediscover identical solutions. Extreme environments, minimal tools, unskilled assembly, maximum strength from minimum materials. When humans finally build permanent shelters on another planet, there's a reasonable probability those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and ruthless practicality. The Quonset hut represents more than clever engineering. It demonstrates how constraints force innovation and how solutions to immediate crises often prove more enduring than anyone expects. The men who designed these structures in 60 frantic days during 1941 were solving a specific problem for their moment. They couldn't know their solution would house millions of people across 8 decades. They couldn't anticipate that the same principles would shelter earthquake refugees, provide emergency housing after hurricanes, or inform designs for extraterrestrial habitation. They were simply engineers, given an impossible deadline and inadequate resources, forced to create something that worked immediately, with no opportunity for revision. That it worked so well, that it adapted so successfully to uses never imagined, that it continues influencing design generations later, these outcomes testify to fundamental truth about good engineering. Solve the essential problem with minimal materials and maximum efficiency, and the solution transcends its original purpose. The curved steel panels bolting together in a Rhode Island warehouse in June 1941 became laboratories in Antarctica, churches in Pennsylvania, homes in Alaska, refugee shelters in Africa, and inspirations for Mars. Not bad for a structure designed to be temporary. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.